Great. Great. So it's almost 2 o'clock and we're getting a pretty good crowd in here for Luigia's talk. So I think we'll give it one more minute and then we'll kick it off. So let's see. Well, great. I think we will go ahead and get started. So I'm really pleased to welcome Luigia Feng to the early career webinar series that the AGU Geodesy section is running here. And Luigia, as probably many of you know already, she's at the Earth Observatory in Singapore, where she's been there for about 11 years, or wait, since about 2011, so more than more than that, as a principal research fellow. And before that, she did her PhD at Georgia Tech with Andy Newman on a whole range of different geodetic studies. Luigia's work is very broad ranging and unusual in that way, and really exciting in that way. So I'm really looking forward to this talk because she's really spanned the areas from exploring a wide range of tectonic and volcanic processes with geodetic data, and now is getting into more the atmospheric science kind of area as well. So she's going to talk to us today about some of the contributions, very multidisciplinary contributions of the Sumatra GPS array in Indonesia. So Luigia, really happy to have you, and go ahead and start. Be great.
Thank you so much, Laura, for the introduction. Thank you very much for this opportunity to speak to the geodesy community, and thank you everyone for coming to listen to me, especially after a failed attempt last time. Today, I'm going to talk about the Sumatra GPS array, and I want to show you why it is a hero network. And first, please allow me to introduce my work experience and the team that I work with on this topic. So in 2011, I joined EOS as a postdoc, and this is my first job and also my current job until now. For 10 years, I was officially in the geodesy group led by Professor Emma, who's always passionate and caring leader, always cares for innovations and collaborations. Under her leadership, I have been fortunate to work with the extraordinary group of scientists within the geodesy group to study the Sumatra tectonics and earthquakes. These people include past group members like PhD students, Louisa, Cho Chiang, Rishav, Reno, who they are now doctors now. Also like the postdoc Eric and research assistant Paul, and an undergraduate student and current PhD student Grace. Throughout the talk, you see their names appear quite often in my slides. In 2021, I joined the Center for Geohazard Observation CGO office, led by Professor Liang Chongyu. So what does CGO do? So CGO is a very unique office within the EOS, which is dedicated to building and maintaining the geophysical observation networks that EOS has in around Southeast Asia. So CGO is like a tiny mini Earth scope, a combination of UNAVCO and IRIS, because CGO manages not just GPS stations, also seismic stations. CGO staff are a group of scientists and engineers. Here, Iwan has been leading the effort of maintaining the Sumatra GPS array. Jeffrey and Pusung, they are very experienced engineering. they have installed many GPS stations, and Nurdin, Tulik, and Danny, all Indonesian. They help out the sugar maintenance. So these people usually are not mentioned in scientific talks, but they are the key people to who make the network running to support the research I do. So that's why I just want to give them a shout out here. In addition to the two groups, I have also worked with many collaborators on the subject. I listed some of the main collaborators here, like EOS founding director, Professor Carrie C., Assistant Professor Aaron Metzner, and Dr. Cal Bradley, and Associate Professor Sivan Barber. And Fabio and Wada, they were PhD students, work with our group. And there are so many others, and I haven't listed here. So all these people I mentioned, I have been just calling names. All the people I mentioned and myself are linked together by this Sumatra GPS array, which has a very sweet name, Sugar. So Sugar is a GPS, continuous operating GPS network in Sumatra, most of them on the western coast of the Sumatra and on the islands west of Sumatra. So for your the sugar really is the main topic of this talk. And so for your expectation of the talk, I listed an outline for the talk. So I do a first overview of the history of sugar. For this part, it's a relative easy topic. You can relax and enjoy the photos. And the second, I will showcase the various types of sugar data. This part needs a little bit of thinking. And the last part, I will illustrate how we use sugar data for addressing scientific questions in tectonic climate science, which needs some bit more thinking. So I start with the history. So the birth of the sugar. So Kerry is not just a founding director for US, he's also a founding father for sugar. Actually, he proposed the idea of GPS network in Sumatra at Caltech. He won the heated debate of getting the fund from Caltech, and he got the money to install a few GPS stations in Sumatra. So here he is. It's very nice to see Kerry drilling the holes. We just recently installed one similar station in Singapore, so this reminds me of good memory. This took a lot of hard work with Kerry, with a lot of Indonesian collaborators and people like John Galaska from US. So Sugar was born in 2002. For those who familiar with UNESCO standards, so the sugar standards strictly follow the best quality of the monument, which we use this shallow drilled braced monument. It has four legs, one in the vertical and 3 tilted legs and bolted to the ground. Such a monument is very stable. So gives us a very precise movement of the crest here. So fast forward in time, here are some of the photos of how the station look like now. You can see the rust. The rust tells the time passed very fast. The rust on the legs, and they are damaged domes and antennas and cables. So maintaining the network is not easy. Here are some more photos showing the team doing the maintenance work in the field. Some of the stations are very remote islands, so they have to take a boat, which sometimes could be risky. And even on the islands, the station are not near the port, so they have to travel in the muddy road by motorcycle to the remote part of the remote islands. And also you have to have some skills, good climbing skills, climb the pole to fix the solar panel. So thanks to them, we now have a very good, rich gold mine of sugar data. Now, sugar is turning 21 this year. So sugar was initially initiated by the Indonesian Institute of Science, LIPI, and Caltech at the time. And now it's joint owned and operated by BRAIN. BRAIN is a new research institute by merging all the very different types of research institute from LIPI. So LIPI is part of BRAIN now. And so we work with BRAIN now. The stations, this map showing the history of the station installation. So move to the scientific question, why we install this network in this location? So let's zoom out to the big plate tectonics. So in this region, the big plates, the Indian superplates, Australian superplates, they're subducting underneath the center plate. So this motion, plate motion is partitioned mostly to two major structures, the Sunda max thrust here and the Sumatra, the Great Sumatra Fault here. So let's look at this cross section here. So when the two plates got stuck right here, during most of the time, the downgoing plates will drag down the upper plate, so causing the station moving downward on the surface. And then once the energy could not hold up anymore, the plate will break, the interface will break, and the plate will bounce back, and the stations will go back up. So the triangles are showing the sugar stations here, and this is aimed to record the deformation of the earthquake cycle. And one thing is particular unique for sugar is it was initiated before the start of recent Great Sumatra earthquakes. So that was really carries a visionary view of why we should have this earthquake in this location. Another particular thing about this location is the Four Arc Islands. So in most other subduction zones, they don't have the Four Arc Islands in this location. And there are observations far back from the change. So we do have a very unique situation here to observe the near megathrust observations. So next one, so how the stations look like, how the time series look like. This is a daily position time series. These are standard daily time series. That's, if you look at the time series, that's very, very different from time series in most other places because it's very busy and you see a lot of signals. And y-axis is time, x-axis time, or y-axis is the position. And the station are mostly oriented from north to south. If you look at them, they are this part, there are raids before the earthquakes, and there are these jumps that are co-seismic offsets, and then huge post-seismic offsets after many different earthquakes. So the gray lines I'm plotting here are magnitude larger than 7 earthquakes in this region. So you see how busy this region has been. So for a long time, my job was like staring at these time series to try to disentangle the different signals, which signal comes from which source. So here we are. We identified 40 plus events in these time series. So this figure is looks very simple, but actually I had to pull out from about 10 papers of different slip distributions. So there's a great effort into just getting these slip distributions. Here, this is the 2004 event, the contour lines here. This is the only event that was not derived by the US groups, and all other events, slip models were derived from US models. So I go through this complicated series of earthquakes. So I go through them quickly to give you an overview here. So this is 2004 magnitude 9.2 earthquake. This is a big one, biggest one, the start, and it's 2 years after Sugar was initiated. So now this one is the 2005, magnitude 8.6. And the next one, this is 2007, magnitude 8.4, and two aftershocks here. So more than that, there's another interesting one, strike slip events in the Indian Ocean Basin. The Sugar Network also see it. These are the great earthquakes. When I define like great earthquakes magnitude larger than 8. If it's magnitude between 7 and 8, I call it like large earthquakes. So there are so many large earthquakes in this region, like these little guys. In any other places will be big, considered one of the biggest, but in here, these are only large, not great. So one interesting part is you see the 2008 here, there's one 2008 magnitude 7.4 earthquake in the north and another one similar magnitude in the south. And same in 2010, there one in the 7.8 in the north and in the south too. This particular one, this is called Mentawai tsunami earthquake. If you look at this depth, it's in a very, compared to the other ones, it's in the very shallow region of the subduction zone. Why it's called tsunami earthquake. So just for those who are not familiar, for tsunami earthquakes, there are earthquakes generate a tsunami much larger than the expected for that magnitude. So a lot of examples are in my following slides. I will use this the 2010 Mentawai earthquake as an example. So okay, so these are the slip distributions, and now let's look at some of the seismic gap here. Okay, after all these events, we still have a seismic gap here, and this area is where where most of our stations are located now. So we are expecting another big one in this region, which we don't know when it will happen. Here, we just look at the daily positions. Here, the high rate. This will give you a sense of what kind of different types of sugar data we have. So for high rate, we have some data for some of the big events, like the one Emma studied, the Mentawai tsunami earthquake, and also the Banyak Islands earthquake. So for the high rate, Diego Marga from University of Oregon gave a very nice lecture last year, introducing how he used a high rate for earthquake monitoring. So I'm not going to give more, talk about more here. So let's move on a different time window. So this is between high rate 1 Hertz and the daily solution. So this is 15-second position time series using kinematic processing. And these circle dots, white circle dots are daily solutions. And these colorful circles are the 15-second positions. What you can see here is, well, if you estimate co-seismic offset from the daily solution, you will probably like do this green bracket here. But if you are looking closer into within the day, then the day co-seismic will be this yellow one here, yellow bracket here. So this is a question really, if you just using the daily co-seismic offsets, you will overestimate the co-seismic component while underestimate the post-seismic component. The post-seismic offset happened immediately after the earthquake rupture, and it's quite significant for some of the events like this Mentawai tsunami earthquake, even within a few hours of the earthquake. So this is work done by Wada, and she also put together some of the statistics in this figure. This is showing you are looking at daily solution, which is blue, high rate 15 seconds, yellow, red, high rate 1 second. So this is a comparison of this three different co-seismic offsets based on different the temporal resolution. What you can see here, these symbols here, circle is high rate 15 seconds, triangle is high rate 1 second, and they are colored by here the percentage of difference. And the x-axis is at the epicentral distance, how far away the station to the earthquake. So the closest ones, really, those have underestimation, significant, about 50% of underestimation if using overestimation if using the daily solutions. Okay, so far I've been just talking about positions, and now just quickly move on another type of signal, ionospheric total electron content, TEC data. So these are for the two magnitude 7.8 earthquakes in 2010. The difference between them is the depths. So the tsunami earthquake, Mantava tsunami earthquake, very shallow at very shallow depths, and while the Banyax Island earthquake occurred at the normal, regular seismogenical depths, and which caused a very significant difference in the tsunami generation. For the Mantava earthquake, the run-up went up to 16 meters and got about 400 victims due to the tsunami. And while for the Banyax Island earthquake, the run-up has only 6 meters. So these earthquakes have the same magnitude. So if from the traditional seismic way, you wouldn't be able to tell which one is has more potential to generate risky tsunamis. But the work done by Fabio, who used the ionospheric TEC signals, is to try to using the TEC data for tsunami early warning. This can be done because you look at, so on the right, these are the TEC time series and also spectral analysis of the time series. And you can see for the Mantava earthquake, there's a very strong signals in the TEC heat map. This is because when earthquake rupture the sea surface will uplift the water column. The water column uplift the atmospheric column, which will create atmospheric acoustic wave, gravitative wave that travel at much faster speed than the tsunami itself. So it travels about 1 kilometer per second for the acoustic gravitative wave in atmosphere. So it will take about 8 minutes to reach the ionosphere. So if we are able to get this signal in the early warning system, and we can tell, okay, there's big signal from the tsunami, then this has a potential for tsunami early warning. I'm just giving a very quick flashback for this study. So now let's move on to the noise. So for many years, I have been looking at positions. Then recently, I got interested in the noise, which has been sitting in my computer for many years. So this noise is the Zener square delay, ZWD. These figures showing how the ZWD signals look like. They are very different from positions. You can see the change is not that big. You don't see the offsets or the post-seismic stuff. You see these dips here and peaks. These actually contain very useful climate signals, which I'll showcase later in one of the examples. So far I've been talking about showing you the types of the sugar data. Now I will move on to talk about how we use the sugar data to address scientific questions in tectonic and earthquake climate science. I will do this by giving you 4 stories. These 2 stories can be like viewed individually, or you can put them together. So don't worry, there might be a lot of information, but I'll try to give you enough background. So let's move on. The first one. So the first one is about sibling earthquakes in a persistent rupture barrier. So just from the title, this very conflicting information. It's persistent rupture barrier. That means the rupture don't usually go through, but why it can host earthquakes, and not just one, but two sibling earthquakes. So this is the work done by Paul Morgan. Here, I show you. So the persistent rupture barrier here is under the central simulu. We see this is the southern edge of this 2004 event, and this is the northern edge of 2005. So this is why we call it persistent rupture barrier. So this is reviewed in Aaron Mausner's coral data for the last 1,000 years. And what he sees is the rupture do not propagate through this barrier in the coral records. So the great ruptures always end at this location, but yet it also has generated two recent large events that's magnitude 7, one in 2002, one in 2008. So for the 2002 event, that was actually before we had a station in this location. So the 2002 was recorded only by coral microatolls for vertical displacements only. So here we don't just use sugar data for all possible data, like coral data, insect data. We'll try to use all of them to supplement sugar data. So for this event, the coral data, these circles showing the uplifts and give us a quite good location of where the slip occurred. And for the 2008 event, so this one was very well recorded by not just GPS, but also INSAW. So we have a very nice, robust location for this event. And if we overlay the two on top of each other, then we can see these two events, they not just occurred very close in time, they overlap each other, but they are not identical. This is the reason why we call them sibling earthquakes. Okay, so if we join profiles, these two earthquakes occur in where the 2004 and 2005 events stopped. And here, Louisa used some of the coral data, derive a coupling map for this region. And in her models, what showing here is the red part is a strong coupled region, while the blue is weakly coupled. So her model show, the 2002 and 2008 event occur in a region that's highly coupled. And why? So why is this patch is highly coupled, and why the two events occur? And there are some marine geophysical data. There's two studies in this region, one from seismic tomography results from Tom, where the orange lines showing, and also another one from seismic reflection results from Frank, the green line showing. So the green line, orange lines here along the profiles are showing there is a morphological high on the slab. So what we propose is the reason why the two events occur here is because this morphological high is this location and create a strong coupled seismic asperity. So just give a summary for this story. So both the two magnitude 7-ish events, they rupture of overlap under central simulu, and where it occurred there is because highly coupled seismic asperity, and this asperity is most likely controlled by a subducting morphological high of the slab. Okay, now let's move on to the second story. So for the second story, it's called nearly all types of slip behavior in a narrow megastrata subsegment. And this is also work done by Paul. This narrow subsegment is a 75 kilometer wide Banyak Island settlement right here. So Banyak Islands is quite unique because they sit back relative to other islands like Simulu, Nias here, and it records. So by combining coral and GPS data, we can have this history of the Banyak Islands go up and down since the last great event before the 2005 event, 86-1 event, magnitude 8.5 here. And well, this is quite a complex history going up and down, which for a large part of the job for us is try to map out the location and type and magnitude of where this slip behavior is. So let's start with the most recent one. So the upper panel here on the left is the model Chuchang derived for the 2005 slip model, co-seismic model. So he used a lot of data, not just GPS, but also core data and ASTER satellite imager data. So this model is very well constrained. And his model showing the two big rupture lobes with a low slip gap in the middle. And something interesting is that for the 2010 event derived by Paul, and right here using the sugar data and also some of the coral data, and the 2010 event fill up this low slip gap left by the 2005 event, just like a puzzle piece, which is very interesting. And this is just the most recent slip history. And if we go back, well, this region is very complicated. Goes through this events here, the history. So panel A, that's showing the different structures, both on the subducting slab and also on the upper plate. So in 1907, there is a tsunami earthquake magnitude 8.2 here in this location, constrained by very historical seismic data, work done by Stacy Martin, and then move on to 1966 to 1981. So Louisa, using the coral data, I found out there is a very long-term 15-year slow slip events in this region that's occurred down dip here. And move on to 2005 and 2004. So 2004 here and 2005 occurred. And 2005 has a lot of upslip, both in the up dip location here and also down dip locations. And there are a lot of aftershocks, which is much smaller earthquake form, like aftershock belt here. And after that, another 2010 event here happened here. So just to summarize here, it's almost all types of slip behavior you can think of max thrust is capable of, you can find here, including great earthquakes like 2004 and this 2005, and also large earthquakes in the sibling earthquake I mentioned, also large earthquake, the Banyak Islands, a large earthquake here, and also tsunami earthquake, and upslip, upper dip, down dip, and slow slip. So this is a very interesting region with such a small, such a narrow segment with so many different types of slip behaviors. Here, if we look at them along the depths, so this is the top is Sonley's depth-dependent rupture domain models based on globally compiled seismic data. So they proposed domains A, B, C, D here. So the slip history in this region into this in domain A is a conditional stable region in the very shallow depths, which upslip and tsunami earthquake occur. Yes, we do find the 1907 tsunami earthquake occur in domain A, and some of the 2005 upslip also occur in this region. Then domain B and domain C, there are have some small differences, and they host bigger events. And for domain B, we see the 2010 Bank Islands and 2005. The big 2005 Nyasa earthquake occurred in domain B, and 2010 event didn't go to the domain C, but the 2005 event ruptured to the domain C. And also the down dip domain D, where host a slow slip and seismic tremor low frequency events. And we also find the slow slip events here. And some of the 2005 upslip also occur in this depths. So for this story, we don't really have a conclusive suggestions why this happened here. So for this and more, I want to introduce you this very useful natural laboratory. I want to call for more research into this region to understand better why it happened this way. Is it because slip history? Is it because the structures on the subduction slab, or is it because fluids? We don't know answer, but I hope there will be more research done from like earthquake modeling and marine geophysics to better understand this segment. Okay, now move on to story 3. So this is my own work, upslip modified by past rupture history. So this is about the upslips of 2010 Mentawai tsunami earthquake. The 2010 Mentawai tsunami earthquake occurred down dip here of the 2005 event. So you see the difference. So in the southern east part, the down dip of the Mentawai earthquake, there is past events already ruptured. So segment already ruptured here. But in the northwestern part, it is still remain locked. That give the two segments are showing a very different rupture history. We have our stations recorded the post-seismic deformation for this event here. So this is a 5-year time series for the event. Just take a note, these are already detrended time series with removed other signals. So before the event it's flat and then showing this post-seismic signal. The co-seismic offsets also removed already from this. So these are the time series I used for modeling, try to figure out where the slip occurred. These 5-year post-seismic deformation has already exceeded the co-seismic deformation. You see these the green vectors, they are much larger than the blue ones. And you also see the direction of the vectors are shifted a little bit, so that it's a suggestion of like the slip centroid have shifted. What I did is I use rate and stay based velocity strengthening models, quasi-dynamic velocity strengthening models to model them. The reason is these, even though these networks are already very close to the event already, but still kind of outside. It's not right above, it's outside. It's outside the rupture. So if we use traditional kinematic inversion models, it will put the slip right underneath islands instead of offshore. But we know it occurred offshore. It's not right underneath. So I used Emma's co-size model to as the initial stress trigger to trigger the models. So I did 2 scenarios. One scenario is simply just use a co-size model as a trigger. And the second scenario is not just using the co-seismic, but also apply some pre-stress conditions to this region, because we know I divided by the region by two domains. One is the southeastern and the northwestern regions based on the slip history. We know the southeastern, their past history of the 27 event occurred here. We know the northwestern part, it's still remain locked. So there should be a difference here. From the pure co-seismic driven model without the stress, pre-stress, this is how the model, the best fit model fit the time series. And once we introduce this, the pre-stress, well, the fit is greatly improved. So this is suggesting, wow, there is a difference in the two different segments need to be considered. So the pre-stress introduced by the past history does modify the upslip. Here is a comparison of the model vectors. So scenario one without the pre-stress, if it's not as good as one with pre-stress incorporated. So the models show the upslip migrate down dip of the co-seismic with cumulative seismic moment to 7.6, which is about 40% of co-seismic moment. It's a quite huge of upslip for this tsunami earthquake. Okay, something more also similar to the Banyak Islands earthquake. So the zones are quite not clear cut here. So this upslip region seem to also penetrate into the co-seismic 2007 region here. This is one model from Kanka, but even we use more recent, the Louisa's model, which is in black. So you can see the upslip does enter the co-seismic zone of the 2007. So the question is, it's not the areas. It's sometimes it could rupture during co-seismic, but they could also rupture during upslip. It's really contradict to previously like traditional sorts of co-seismic upslip occur surrounding the co-seismic regions. Okay, that's fine. And this little 17.2 Reno's earthquake occur like on the border of the co-seismic, the upslip region. Okay, that's give a summary of the past history. So I showed the 2010 Mantawa earthquake, upslip modified by the history of the 2007 rupture. Next, the last story, I will talk about a very different topic on climate. So this is my own work too. So I want to show you how the sugar data can see the monsoon variations and extratropical dry air intrusions. Here, just to give you some background how the Zenith weather delay works. So when we use the precise positioning point, PPP positioning, and we will estimate the Zenith weather delay as a byproduct. So the Zenith delay, the total Zenith delay can be divided into Zenith hydrostatic delay, ZHD, and Zenith weather delay, ZWD. ZHD is quite parameter can be very well predicted. So we can, if you given the pressure. So this one's well known, but for ZWD, it's less well known, and you have it varies. And ZWD give you the information about how much water vapor in one atmospheric column. So I use the ZWD. So the DWD can divide derive into perceptible water vapor PWV, which is the amount of water vapor in an atmospheric column. So there is a relationship using pi here. So, but this pi for our region is very constant. It's a constant here, not changing much. So basically, the byproduct directly from PVP positioning, ZWD, can be used as a proxy for the PWV here. What we did is we looking at intra-seasonal period. This is different from many other studies, which you looking at the long term, getting the rates from the PWV or looking at the diurnal cycles. But we are looking at a very special temporal domain that's intra-seasonal, which not many people look at. Here, this is the station listed here and in 2008. Okay, so what I did is I decomposed these time series, PWV time series, into using the empirical orthogonal component EOF. If you don't know EOF, EOF is term used in climate science. If you don't know EOF, this is the same as principal component analysis, which is well known in geodesy. And so I use this method to decompose the components into two major modes. The first EOF mode here is, you can see the blue circles. So this is a big signal that covers the whole network. But for the second mode, here is, you see a lot more stronger signal for the southern stations and less signal for the northern stations. So next step is try to figure out what are these modes, the physical mechanism behind the modes. So for the first one, it's quite obvious it should be monsoon, because even for us in the tropics, the sun also passes over us twice a year. So that introduced some monsoon effect. So, but which one? The most well-known one is the Indian monsoon right here. And also there are some other monsoon systems like this Western North Pacific monsoon and Australia monsoon. And for us, the sugar data is in between these three monsoon systems. So which one is calling the first mode? So I did lead lag cross correlations of the first mode, the time series of the first mode with the Indian monsoon index and also the Western North Pacific monsoon index. And what shows here is the red lines gives you the highest cross correlation at 3 days monsoon leads. So the Indian monsoon lead the changes of water vapor over Sumatra 3 days earlier, while the Western North Pacific monsoon is 3 days later. So it's clearly the Indian monsoon is driving the changes of water vapor over Sumatra. So, so the westerlies, the winds westerlies coming from the Indian monsoon, and then will in fact going this way, going towards the east, and will impact the water vapor over Sumatra. And also these two monsoon systems are related to. So that's the first mode. So for the second mode, dry air intrusion. For the second mode, I took the highest, so the strongest day of that, the strength of the second mode, which is on the 2008, July 23rd star here. And I did back trajectory of try to trace back where this air comes from using back trajectory models here. So look, the dry parcels can be traced back to southern atmosphere going backward this way. And then here they descend. So along this way, they descend. So they descend from upper troposphere to middle troposphere, from upper troposphere in the middle latitudes to middle troposphere in the tropics. And along the way, the relative humidity stay very low. So in the tropics, the moisture is usually quite high, but in the mid latitudes, the airs are usually low. But these dry air stay relative dry and traveled this way towards the equator. And if looking at the potential temperature, so what is the potential temperature? The potential temperature is the temperature of air parcel has if it brought to the sea level adiabatically, which means along the process, there's no heat generation, heat loss. You can see the air parcel as like closed system. They travel from mid latitudes of the upper troposphere to upper troposphere of the middle latitudes to middle troposphere of the tropics. Here is a model showing the potential temperature, how it works. If you find 330 here, yeah, this illustrates. So this is the altitude here from middle latitudes to go down. Along this equal potential temperature, the air parcel travels, but without changing much of the humidity. So that's how the dry air can be brought from the middle latitudes to the tropics. So what is the behind fundamental reason how this dry air intrusion occurred? This is because Rossby waves. Rossby waves, if we the best illustration Rossby waves are the these waterlies, the strong westerlies. You can see the Rossby waves are caused by the rotation, no rotation, no Rossby waves. So the Rossby waves are caused by the Coriolis force at different latitudes, and then the fluids, including the air in the atmosphere, travels along the rotating Earth. You do this curly Rossby waves. So in here in the study, we show the dry intrusions are caused by the Rossby waves. This figure here is showing the regressions with the second mode, with the potential vortices and also the winds. If you look at the winds that's going this way and brings the Rossby wave goes this way and brings the dry air to the sugar latitudes. Okay, so that's the end. So a summary for this fourth story is we know the water vapor over Sumatra is driven, the intra-seasonal variability driven by the Indian monsoon. And the second influencer is the dry air intrusions due to Rossby waves propagating along the southern hemisphere. And the implication is the tropical extropical teleconnection, which is quite a hot topic in climate, is the climate here is definitely influence related to the southern latitudes. Okay, so I'm going to wrap up my talk. So I've shown that sugar was initially built for tectonics, but it has a much bigger impact, greater impact. I hope this is talk really is early career of sugar through my eyes, but different people working on sugar data will give different stories. I want to show you that sugar is how useful and how a hero it is for the tectonic climate studies. Thank you so much for your time.
Great, thank you, Lucia. That was a really amazing talk, and I'm like blown away by how complicated the GPS time series is that you guys have to deal with. That's incredible. You guys have done an incredible job trying to figure that out. So I'm going to allow people to ask questions. I'm trying. let them unmute themselves if they want. If people could raise their hands, they have some questions for Lucia. I'll try and keep an eye on that here. I guess I have a first. Oh, okay, we've got Matt. Matt's raised his hand. Matt?
Great, thanks so much, Lucia. That was a great talk. I guess after all these great examples you showed, I guess my question is sort of the future of the sugar array. I mean, is it something that you think is sustainable going forward? Are there ideas about improvements or modifications that could be made? I'm sort of in particular thinking about, I don't know if it's even a possibility to think about things like early warning using that network and things like that. I'm just curious about what the next step might be.
Yes, it's a really great question. So it's also the question have been in my mind for many years. In terms of future, definitely I have been using GPS throughout the talk. That's really because we mainly just use the GPS signals. So not GNSS signals. So that will be the next step. Upgrading to a system that can use multiple constellations. Also for the funding, EOS is at the end of the internal funding supported by the Singapore government. So we have secured a few years of external funding to support the CGO office, also the maintaining the networks. So that's good news, but for longer term, I think the future is we need to demonstrate to Singapore government that how useful it is. That's why we need also help from the international community. So if you guys use any of the sugar data, do any research, just drop an email, like a publication of these. I have been compiling like studies, research study, not just from US, but also external studies that have been using sugar data. So these are very good examples. If we show them a list of publications, how useful can be, that's more likely we can get continued support. That's for internal funding and also upgrading. For real time, okay, real time there was quite difficult for the remote islands, because back like 20 years ago, even you don't have cell phone. So you don't have a cell phone, like it's very hard to transfer the data back. We used Beacon for a long time, which is a satellite system, but Beacon only works like once a day. So you can download the data. Well, if that event happens, you can download the data once a day, but it's definitely not real time. But recently, the team, they introduced a new satellite system called MiniVisat, which is cheaper, and I think they're going to install more MiniVisat for more stations. But I think things are changing for the better, because last year when Ewan was doing field work in the Mantawa Islands, an event happened in Java, and I just messaged him in WhatsApp, wanted him to download the data for the Java event, but he was able to download data in Mantawa. So I think it's changing. It's after 20 years that the remote islands are like become less remote now. And I have the hope that in the maybe next 10 years, it will become possible, like all the internet and the setup, like what we can do in big cities. I think I have this hope for the future. So in that way, then real time is possible. For now, real time is not that possible. Okay, thank you for the question, Matt. Yeah.
It's good to hear the vision for the future part of the network. So Kellen Wang's got his hand up for a question. And I have enabled you guys to put your video on if you want to. So.
Yeah, sure. Why not? Yeah. Thank you, Lucia, for a very comprehensive review. Oops, what happens to my video? I cannot turn it on for some reason, whatever. Yeah. Anyway, I have a comment and a question. The comment is, given that we know a fault patch can exhibit a dynamic weakening at high slip rate and a velocity strengthening at low slip rate. And so it's no longer surprising to see the same fault patch that behaves differently in different events or even in the same events. Yeah, but it's very nice to see it in action, right, with real observations. So it's beautiful work. Thank you for that, and for sugar. And the question is, what is the prospect of extending sugar in a way offshore? So what's the progress in seafloor geodesy in that part of the world?
Okay, thank you, Kellen, for the comment. Okay, so for the comment, yes, I think we have done all the kinematic models or the sleep models, but the next step is definitely we need more physics, earthquake physics-based models for the Sumatra events that will address, Kellen, your question of figuring out this the different rupture, the properties of different areas. And for the offshore geodesy, we don't have a current plan yet for offshore. Shinji, one of the seismologists, he might want to put some of the ocean bottom seismometers if he gets the funding, yeah. So, but for wave gliders, we don't have a current plan for this region. One reason is that area in terms wave, it's quite big wave. So Mantawa Islands is a very popular surfing spot for surfers. Yes, and but yeah, something to think in the future. Yeah.
So Cindy has their hand up.
Yes, thank you, Lucia. Thank you for your talk. I would like to know if the atmospheric studies you're working on can derive in tropospheric models for INSAR data corrections.
I think it's possible if the GPS network is dense enough. But the one issue is our network is mainly over the islands where the INSAR has like less capability. If the mainland, if it's on the over the mainland, I think possible. But the density of our network over the mainland Sumatra is not dense enough. But they actually the Indonesia has a very dense network over Sumatra. They started a few years ago. Yeah. So it's possible. If we can get the data from the Indonesia side.
Sure. Okay. Thank you. Thank you so much.
And Mohammed, do you have your hand up?
Thank you, Lucia, for your great presentation. My name is Al-Kausar.
Hello, yeah. You have a question?
Yeah. You have your hand up.
Hello.
Hello, do you have a question?
Okay, I will write in the chat, yeah.
Okay.
I have problem with the connection.
In the meantime, Lucia, I have a question. So Sumatra's always seemed kind of unusual to me because it's one of the few places where there's not a whole lot of evidence for slow slip events, except for I guess the long 30-year event that they saw in the corals.
Yeah.
And I guess, do you think that's probably there are slow slip events there in normal times, but that we're just in a period that's so dominated by post-seismic processes that we're just not seeing that sort of behavior? We're not in the right point in the earthquake cycle, or what do you think? Or is there some other evidence that you've seen that you haven't had a chance to talk about today?
Yeah. So I think part of the reason, of course, is because the rupture zones they saturate with upslip already, so there's not much room for slow slip. But they are, in addition to the coral ones, let me see if I can go back to the time series. Okay, here. So another reason I think is still our network is not dense enough. So if you look at this, there's MLKN. MLKN is a station in one of the very southern islands. Let's see, I can't find the map. Okay, so here, MLKN is this light blue guy here. This light blue guy. Okay. So you see, in the vertical. Well, it's going down. It's nicely going down. And this is not the post-seismic signal. It's quite far from the the events already happened. So while the horizontal signals you cannot really see here, but if we decompose the trench normal and the trench parallel component, the trench normal component is very small. So there was a dilemma, like, why is this station going down? Which then we think if it's going down that much, then it's locked. It should be locked and a lot of interseismic. But why the horizontal vectors are not going like away from the trench? So Rishabh came up with a theory explanation. So his explanation is there was a slow slip happening here, but the slow slip is canceling out the horizontal component, but not really much. The vertical component is actually doubled, the two effects, but the horizontal is canceled out. But we only have one station, and it's hard to confirm anything. So I think we don't really see, like, definitely not Cascadia-like slow slip that's so frequent. Otherwise, we would have seen. This is probably because it's saturated already by F slip. But there should be events that, due to the limitation of network, we couldn't really confirm.
We still have to wait a little longer into the earthquake cycle and see what happens next.
Yeah,
Another
maybe
reason
we need
to
a
keep
even
this
more
network
station.
going. So we've got a question in the chat from Mohammed Al-Qatsar. Are all GPS stations equipped with accelerometers? And this is thinking in terms of earthquake early warning.
Currently, no, but we do have, like, I think 11 seismic bunkers already built in around the Mantauba area, because that's the gap we are expecting a big event. So in that area, the plan is to put broadband seismometers co-locate with these GPS stations in the seismic bunkers, but that's not done yet. But that's work to do or to be done in the future. Yes, in the short term. Yeah,
Getting the
Yeah.
data in real time, or as real time as
real
possible.
time. Yes,
or
real time. Yeah, for the stations on the western coast of Sumatra, it's all possible because they have very good internet already, and we use the FTP to push. It's the main issues are the station on the islands.
So we'll have one last question before we wrap up, and thank Lucia for a really fantastic talk. Satria Muhammad Ali, you've got your hand up. I'm going to unmute and ask your question.
Hello.
Hi.
Hello.
Okay. I am Satrio from the university in the southern Sumatra, and currently doing PhD in Taiwan. And currently I work in the Sumatra, and I experienced that the sugar is very powerful. However, combined with the Indonesian station, the network is far from dense. It's still very sparse, the distribution. And I have a question that, is there any plan to install more station, especially in the southern Sumatra, and maybe we could do collaboration to build the more station in the southern Sumatra, because from most of the research you show here, and from the other publication, most of them are in the north and the central Sumatra, and the southern Sumatra is very less discussed. Thank you.
Thank you so much for the suggestion and invitation for collaboration. Yeah, southern tip of the Sumatra, we had several stations, but vandalism, so some of them die. And that's the area it's under studies now, but it's still very interesting. So that will be related to Sumatra fault. So something I didn't really talk about is the Sumatra fault, which Reno has done a lot of work. Sugar actually recorded several events on the Sumatra fault, which has more like higher risk of hazard because it's on land. It's not. It's directly on land. I think for station expansion, we'll see. We'll see. We do have plans like for sea levels. So we want to build more stations, then can look at that using the GSIR to look at sea levels. I always want to do like multi-purpose, so station for sea level and southern tip of Sumatra could be a location. Both look at the sea level and also look at the faults. Yeah.
Great. Sounds like a lot of work needs to be
Yeah.
done and a lot for the future. It'll keep you guys busy.
Yeah, it's always not enough stations. We always like budget, not enough budget. We want more stations. Yeah.
Yeah, definitely. Well, it's a worthy place to be investing in that. So.
Yeah.
So if we could thank you, Lucia, again, I wish you could hear the applause because that was a
Thank you so much.
fantastic talk. Thank you so much for giving us the talk. And I just want to remind everybody on the 30th of March, we have our next early career webinar from Xiaoxuo Liu. Kaust, who's going to be talking about hunting for tectonic and climate signals, GPS position time series. So keeping on this theme of GPS for tectonics and climate, and he's going to be giving that on March 30th. That's US time, 12 p.m. Eastern time. So, and thank you everybody for joining us for this fantastic talk.
Thank you for your time. Bye-bye.